Hello, I'm Václav Novotný and welcome to the tutorial of Decentralized Systems 1. This tutorial will be focused on microturbines, the fundamental device of combined heat and power production in decentralized energy systems. So what are the microturbines and how does it look like, what does it do? So from the user perspective, it's a box to which you connect a natural gas pipe and you get electricity and heat out of it. So it looks somewhat like what you can see here on the left side, on the left figure, where you can see really it's all the technology is covered in the box, which just has some air intake. Then in the back might be partly visible, there might be some stack for the flue gas outlet. There are wires for the electrical output, and there would be pipe for heating up the water for providing the heat. What is happening inside and what is the core of the technology is seen on this figure on the right side, where you have the air intake. The air intake goes actually around the electrical generator to provide some cooling. Then the air is here in the compressor, compressed to and pressurized to higher pressure with pressure ratio typically about, let's say, 2 to 5. Then it goes So the air goes around the generator for cooling. Here, just partly visible radial compressor, single stage. The air goes through recuperator, we will talk about that a bit later, into this, basically a can, which is a combustion chamber, where there is a fuel inlet. The temperature increases. This gas at the high pressure and temperature goes to turbine, again just typically single stage radial turbine. Then the flue gas goes out here through something called recuperator and outside of this microturbine itself, where of course the turbine with the compressor on the single shaft have some network power output, which is in the generator converted to electricity. Then this flue gas exiting the system still has considerable temperature, and the heat of the flue gas is used for typically heating. Now let's have a look at the whole system in the diagrams. So we have the inlet of the air going to the compressor, which pressurizes it. Then here is the recuperator that preheats the air before the combustion chamber. Therefore, it saves us some of the fuel input. In the combustion chamber, the fuel is combusted with the air. Temperature increases further on to the highest point. At this point, the high pressure, high temperature flue gas goes into the turbine, where it expands, creates the work. Part of the work is consumed by compressor, the rest of the work is converted to the electricity by generator. And before the flue gas exits outside to, let's say, for example, the heat exchanger for providing the heat, it goes through the heat recovery recuperator. Now let's have a look at the system at the TS diagram. So we are starting at ambient temperature, ambient pressure, going to the compression. You can see that the isobars here are relatively close. Here we have pressure ratio of 3. So it's kind of like low compression and looks a little bit like in noodle-ish shape. So 1 to 2 is real compression. Ideal compression would be ideal compression would be isentropic process. Real compression goes to the higher entropy. Always the real processes increase the entropy. So going a little bit to the right, which results in higher power requirement than in the ideal case. Then we have the heating of the air in the recuperator. This heat 2 to 3 is the same amount of heat as heat from the 5 to 6, which we will get to in a moment. 3 to 4 is increasing the temperature in the combustion chamber. You can also see that from 2 to 4 the pressure is gradually decreasing. That's because this diagram considers that there are some pressure losses in the both heat exchanger and in the combustion chamber. Then from 4 to 5 we have expansion in the turbine, where again ideal expansion would be isentropic process going vertically, and since it's real expansion, so we are going to higher entropies and getting also less of the work output. You can see that if we would go vertically, we would have this 4 to, let's say, ideal case of 5 would be longer line than just going 4 to the 5 little bit further right because of the shape of the isobars. And then before the outlet, this still very high temperature heat is transferred in this recuperator 5 to 6 to 3 to 2. Then at the point 6 there is outlet of the flue gas from the microturbine system itself, and it can go to heat recovery heat exchanger for, as I mentioned, for example, heating processes. But also you could have for some other thermodynamic cycle getting some extra work, extra electricity. Now we will build a thermodynamic balance model with the following assumptions and parameters. We will consider in all of the systems to be real dry air as working fluid. That means both before the combustion chamber and after the combustion chamber. This assumption is not that far away from a real case because the air to fuel ratios in generally in combustion turbines are relatively large. Then we have some boundary conditions: ambient pressure and temperature. That means the condition at the point 1. Then pinch point in the recuperator. That is the minimum temperature difference between either point 2 and 3, or 5 and 3, or 6 and 2. The smaller one of them. Then the temperature in the combustion chamber will be 850 degrees C. That's the highest temperature in the cycle, here before the entry to the turbine, point 4. Then we will have the pressure ratio of 3.8. Efficiency of the compressor 80%, efficiency of the expander 85%. In all heat exchangers and also in the combustion chamber, we will assume that there is pressure drop 8% of the absolute pressure. And last but not least, efficiency of the generator and all electrical systems will be 85%. This 85%, it's not just efficiency of the generator itself, because these systems have typically very high rotational speeds, tens to even hundreds thousands of RPM. So you're typically having a permanent magnet generator creating very high frequency voltage, and this typically needs to be rectified and by some inverters or other electronics converted to regular voltage and frequency which we have in the power grid. Yeah, and the model will be, of course, a steady state, and we can get to it. Now I will just review that we will use coolprop for the fluid properties, where the main function which we will be using is props SI, and the names of the major parameters like enthalpy, entropy, temperature, and so on, they have keywords in the dialog box for the function input over here. So, in order to calculate this model, we will build in, or show how to build in Microsoft Excel with the coolprop properties. So here on the top I have the boundary conditions and the provided parameters, so the minimum pinch point, combustion temperature, ambient temperature, pressure ratio, ambient pressure, the working fluid, efficiency of the compressor, expander, pressure drop, overall electrical efficiency, and lastly, I did not mention it in the problem statement, we will calculate the system for having net power output 75 kilowatts. So let's build a table where we will have nodes for each, we will have one row for each node of the system, so going from 1 to 6, but also we will have additional nodes 2 and 5 with the notation IS as isentropic, and those will be ideal cases after ideal compression or ideal expansion after compressor or after the turbine, and those will be auxiliary parameters which will help us to calculate the real parameters at the outlet of the system of the components. So what is given and provided? We know the ambient condition, which is the 15 degrees C. You can probably highlight it also here. Ambient pressure being 101 kilopascals. And we know the combustion temperature being 850 degrees C. Now, because the coolprop calculates in basic SI units, so I have also here the columns with the basic SI units, Kelvin and pascals for the pressure and temperature. So just convert degree C to degree Kelvin. And pascals, like this. Now, what can we do next? We have the pressure at the point 1, and we have the pressure ratio of the compressor, 3.8. So that means that after compressor the pressure will be 3.8 times higher. So pressure at the point 2, isentropic or real, is pressure at point 1 multiplied by 3.8. And this is the pressure to which we want to get after compression, so it will be same for the ideal and real case. Now the pressure at point 3 is after the heat exchanger, so normal, if we would assume that there are no pressure drops, so it would be the same. But in our case, it's not the same anymore, because here we calculate with the given pressure drops, and the pressure drop is 8% of the absolute pressure. So that means the pressure 2 times 1 minus 8%, and we get the pressure at the point 3. Now the same thing can apply for the combustion chamber if we would assume that there would be pressure loss, but let's simplify in our situation that the main pressure loss is happening in the recuperator, because it's heat exchanger with gas and still relatively low pinch points, and high volume of the flow, while the combustion chamber compared to this heat exchanger should have relatively negligible pressure loss. So you will say that at the point 4 is the same pressure as at the point 3. And now we are in front of the expansion. Now we don't know at first what is exactly the pressure at point 5, especially when we consider the pressure drop in the second pass of the of our working fluid through the heat exchanger. But we know that the point 6 is again at the ambient conditions, so we know that. And then the pressure at the point 5 will need to be higher, and pressure at the point 5 multiplied by 1 minus the pressure drop will be the pressure at the point 6. So that means that the pressure at the point 5 will be actually pressure at the point 6 divided by 1 minus and the pressure drop. And I noticed I have it mistaken here. No, it should be correct. So that is pressure at the point 5, and it needs to be same also, of course, as pressure 5 isentropic, because it's just auxiliary helping value, where both of them, 5 isentropic and 5, would be corresponding to the same isobar, same pressure level. So we have pressures in the whole system, and now let's get to the rest. Let's get the enthalpies. So function props SI, where the outlet is enthalpy. We already have here joules per kilogram, basic SI units. And the parameters which we will use, it's at all points of the system it's a gas, so we can always use function of pressure and temperature. So pressure, T as temperature, and we need to specify the working fluid, which is air. and I will use this function again, so I will log the air by F4. So we have the parameters here. We can use the same for the point 4 entrance to the entry to the turbine. Now how to get the parameters after the compressor or after expander. That is where we will use at first the isentropic process, and then correct the isentropic values to actual real values. So for the isentropic values we will need to get the entropy. So the function goes similarly as the enthalpy. Let's put it like this. Copy the whole function. So it still stays as the function of temperature and pressure for air, and just instead of enthalpy we will use entropy S. We can immediately use the same function for the point 4, temperature and pressure. And now what do we now, or how do we handle the point 2 isentropic after ideal compression? Well, since it's called isentropic, with ideal compression that is isentropic change, so that means that the entropy will stay the same. Now for this auxiliary node we have entropy and we have pressure. Those are two thermodynamic parameters which define the thermodynamic state, so we can use them to get enthalpy. So I will again just modify the function of enthalpy from previous part. So we want enthalpy as a function of pressure, with the pressure in here, and then it will not be temperature but it will be entropy over here. Again, same goes for the outlet of the expander. And now we can get the real parameters after the compression or after the expansion. So let's talk a bit about the efficiency. The efficiency of basically anything is always the ratio of output, what we get, compared to input, what we have to put into the system. So for the turbine, the isentropic efficiency of the turbine, you can also put eta turbine isentropic, so is the ratio of what we get out of it. So let's say work real divided by work ideal. What is the work in adiabatic process is the difference in enthalpies. So it will be delta enthalpy. Again for the real expansion divided by delta of enthalpy for ideal expansion. And now let's have a look at it once again. What is the difference in enthalpy of the ideal expansion, where we had the, let's here. So for the expansion, the difference in the expansion for the ideal case would be 4 to 5 ideal or isentropic, and real case 4 to 5 real. So delta H real is H4 minus, minus H5 divided by H4, the inlet stays the same, to the turbine, minus H5 isentropic. And now let's have a look at this equation. We know the specified efficiency of the turbine. We know the H4, that is the inlet. We know the H5 isentropic for the ideal outlet. So the only unknown is the H5. So from that we can get the H5 equals, and now it's the H4, the inlet of the turbine, minus, and now the ideal difference of the enthalpies multiplied by isentropic efficiency of the turbine. Similarly, it will go for the compressor, but in case of the compressor, the ratio, because what we want to get is not the work, but to compress the gas into some given state. So here will the ratio be quite opposite, that it's the work ideal divided by work real. Also, the work ideal of the compression, you can imagine that it will be smaller compared to the real required input, because this is the input, output to input, so the real input will be higher. So here we just again change the subscripts. And the compressor is between state 1 and 2. So it will be enthalpy 2. And here we are talking about ideal, so enthalpy 2 isentropic minus enthalpy 1. That's the ideal difference in the enthalpies, and the real difference in the enthalpies is the H2 real minus H1. And again, we know the efficiency of the compressor, we know the isentropic state, we know the inlet, and the last parameter, the only unknown in this equation, is the H2. So the H2 is, if we do the manipulation, H1, and now plus the ideal difference in enthalpy, and now divided by the efficiency of the compressor. So here we are starting at the point 4, and the point 5 is at higher enthalpy than would be the ideal. We have the difference in enthalpy, which is then smaller than in the real difference in the enthalpy is smaller than the ideal. And here after the compression we get to higher temperatures, higher enthalpies, so we get the ideal enthalpy that is then larger because of the efficiency of the compressor. Okay, so let's go back to our model which we are building. So the enthalpy at the point 2 was enthalpy at the point 1 plus now the ideal difference in enthalpies, H2IS minus H1, and now divided by efficiency of the compressor. And you can see that we get enthalpy higher than the enthalpy at the point 2. Also, especially for ideal gas, the enthalpy is, or a perfect gas, the enthalpy is proportional to temperature. So you can see we are also ending up at a higher temperature than just if we would go to the same isobar isentropically. And now for the expansion, we are expanding to a little bit higher pressure than the ambient, but the enthalpy will be the enthalpy at the inlet, H4, and now we are subtracting from that the ideal enthalpy difference, but the real enthalpy difference will be smaller because of the efficiency. So that's this. Okay, so we have the points 2 and 5. After compression, after expansion, with respect, we have the enthalpy, we have the pressure. Those are again two thermodynamic parameters which are completely defining the thermodynamic state, and we can use these two to get temperature. So the temperature will be function props SI with the we want temperature as the outlet, and input will be pressure and enthalpy, and working fluid, of course, the air. And converting to degree C, we can see that after the compression at the point 2 we have temperature 181 degrees C. The same function can be used at the point 5, and we can see that from 850 degrees C we expand to 606. Now what to do about the recuperator. In case of perfect gas with constant specific heat capacity, there would be the same temperature difference between 5 and 3 and 2 and 6. So first let's model it like that. That means we know the point 5, and point 3 has to be smaller because we have the specified temperature difference, and the heat by the second law of thermodynamics flows from the hot body to the cold body. So the temperature at the point 3 is temperature at the point 5 minus the specified temperature difference. And similarly, how much heat we can extract and what will be the 0.6. The 0.6 would be temperature of the point would be at temperature higher than 0.2, so that that's the point where still the heat flows from 6 to 2 within the specified temperature difference. So temperature 2 plus 20 degrees C, because temperature 6 has to be higher. The heat flows from 6 to 2. And so that we can use it later on in the functions, so we get the temperatures also in kelvins. And now we are missing for these 2 points respective enthalpies, and at these points we know the pressure, we know the temperature, so it's easiest just to copy the enthalpy function, for example from the first case where we also use the pressure and temperature. Okay, so now we have all the nodes in the system. It looks like everything is calculated, but let's have a look at something, because now we are using the real gas properties, not ideal gas, and definitely not the perfect gas, so the specific heat capacity will not be constant. So let's see how much heat we transfer between 0.3 and 2, and if it's the same amount as between 5 and 6. So let's write some Q, parameter Q recuperated. Let's have units. Let's have the same as heat. Enthalpy joule per kilogram. And between the point 3 and 2 is the difference in for the isobaric and these quasi-isobaric processes, the transferred heat is difference in enthalpies, same as for the adiabatic processes, the work is difference in enthalpies. So you can see that the enthalpy is really very useful variable, very useful property. So difference in enthalpy is 3 to 2, and at the second side of the heat exchanger, because the heat transferred from one side, neglecting any heat losses, has to be the so the heat transferred from 5 to 6 has to be the same as the heat input from 2 to 3. So 5 to 6 here, H5 minus H6, and we can see that the values are similar, but actually here from 2 to 3 the amount of heat that we can that the air can intake is actually a little bit smaller. Let's put it like this. So we can see that it's 432 kilojoules, while if we follow the pinch point, only the pinch point which we have specified on both sides of the heat exchanger, so 5 to 6 would transfer more heat than the 2 to 3 can actually take in. So what we can do about that? Well, the limit is at this point 2 to 3. Because it's smaller value, we cannot put more heat between the points 3 and 2 than is in here. So this will stay the same, but we will do something about something about this. What will actually happen is that as we used here the temperature difference 20 degrees C, so it will not be that, but it will be a little bit higher. So let's put this cell into the blue, which will be the iterative cell. So it will not be 20 degrees C, but it will be higher. So if we, for example, try to add plus 1 degree Kelvin, it will still not. It changes a little bit. 1.5. We have almost the same value, so you can see it's not much of difference. But what if? We want to calculate it exactly, and for that we will use the function of solver. If you don't have this function of solver visible in your Excel, so you can just Google for adding solver add-in into the Excel, and you definitely will find how to do it very quickly and easily through options and add-ins. So this, and now the objective will be this cell, the amount of recuperated heat, which will be at the value of here 432,286 joules per kilogram, and we will be changing this blue cell. So let's have it solved, and we can see that the resulting value is 202.7. Before we had 201.2 by the default temperature difference, by the default pinch point. So yeah, roughly 1.5 degree Kelvin or degrees Celsius higher than the original estimate. And by this we have calculated successfully the parameters in all nodes of the cycle. And now let's get at the other parameters. So the compressor work is the work between points 1 to 2, which is required by the compressor. And as we mentioned several times, the work of the adiabatic process is difference in enthalpies. So it will be enthalpy 2 minus enthalpy 1. And units joules per kilogram. Work of the expander is again difference in enthalpies. Enthalpy at the expander inlet H4 minus enthalpy at the expander outlet H5. Now what will be the network of the system? The network is nothing else than the difference in the part that produces the power, the expander, minus the component that is using the power, that is eating part of the turbine output. Now what is the heat input into the system? the heat input is this part called combustion heating between points 4 and 3. So difference in enthalpy is H4 minus H3. Just if we did not have the recuperator, so you can see how much larger would be the heat input, because it would be H4 minus H2. So you can see how much of the heat input the recuperator actually saves. Yep. Now, what is the efficiency of the cycle and of the system? First, let's put together the efficiency of the cycle itself. Because this is also work of the cycle. And the efficiency of the cycle is what we get out of it, net work, divided by what we put into it as heat input. And we can see that efficiency of this electrical efficiency, the thermodynamic efficiency of the cycle is almost 37%. Now we had some specified electrical efficiency of the generator and other electrical system. So what will be the electrical power output? It will be the net work of the cycle itself. This is just the cycle, and then multiplied by the electrical efficiency. So the electrical efficiency of this microturbine would be then the electrical power output divided by heat input in the fuel, which stays the same. And we can see that from 37% we drop down to we drop down to 31%. For very small and compact systems, still not that bad. So these are the, let's say, electrical parameters. And yeah, before we continue, so let's have a look at what is the heat content in the flue gas going from the point 6. So we could call it Q flue, and it would be the difference in enthalpies of the outlet, 0.6 minus, and now enthalpy when we cool it down to ambient condition. And we actually have the ambient condition already here at T0 at the at the air intake, so we don't need to calculate it separately. And yeah, we get this value. So now let's have a look at the heating part where we will use the heat of the flue gas exiting from the microturbine. So at first, let's have a look at what would be the thermal efficiency in case that we would be able to use all of this heat. Well, since the energy balance must work, so it should be 1. Let's see. Or let's say not thermal but eta overall. So the overall efficiency would be all the outputs. That means in case that we would calculate with the just thermodynamic work output plus the heat in the flue gas divided by heat inlet, as you can see, we indeed get 1. But in this system we had some electrical efficiency of the generator, so immediately we will need to use the electrical efficiency, and suddenly we can see that the overall efficiency would be just 94.5%. I will move this over here so that we have later more space. Yeah, this needs to be noted for calculations with derived from the theoretical models, where we can assume the work output as the difference of the heat input and heat output. So just be careful if you have some other efficiencies on the work outlet further on. You cannot just use simple heat input and heat output, because there are some heat outputs hidden. Where is the heat output hidden here? Why we could not use the work, the net work, as the heat input minus heat output here. Let's say this heat input here minus heat rejection here. You can see that here the values are the same, but because of the electrical efficiency of the generator, there is another stream of heat, the waste heat from the generator at basically ambient temperature, which cannot be used for anything, but it's there. But anyway, the overall efficiency we calculated here, we assumed that we would be able to use all the heat in the flue gas outlet. But that's most likely not going to be the case, because we cannot cool down in heating systems, we cannot cool down the flue gas back to the 15 degrees C. So let's assume that after this heat exchanger we are able to cool down the flue gas going to the stack to 90 degrees C. That might be a reasonable estimate for relatively large heat exchangers, and let's say heating just heating water to maybe 70 degrees C. So if we have 90 degrees C here, for simplicity we will assume that there is no pressure drop in this heat exchanger, otherwise we would need to recalculate the whole model. So we have temperature, we have pressure, we get enthalpy from that, and in the calculation of the heat in the flue gas, now we will use this point number or node number 7. And suddenly you can see that the amount of heat in the flue gas which is recoverable is much smaller than before. Before we had 190 joules per kilogram, now we have just 114. What did it do with our overall efficiency? Thermal output plus electrical output, it dropped to about 70%. So just so that we are complete with everything, let's also calculate separately the efficiency of using the fuel for heating. So let's call it eta thermal efficiency, and it will be this recovered heat from the flue gas divided by the heat input. And you can see that that's about 38%. And of course this overall efficiency must be the same value as either this, getting it from the work, same as getting the efficiency of one product plus the other product. In this case, when all these efficiencies are related just with the single heat input. So eta thermal plus eta electrical, eta thermal plus, where do we have it? Yeah, here, eta electrical. And you can see that we have the same, I should have put it here, we have the same numbers. And the last thing that we will do, we had the work output of 75 kilowatts, and also we will say that our fuel will have heating value of Qn of the, let's say, natural gas will be 40 megajoules per normal cubic meter. So we will calculate the mass flow rate of the air going here within the cycle. And now the absolute work output, let's put it here. Absolute work output is unit work output in, for example, the joules per kilogram times the mass flow rate in kilograms per second. So getting the mass flow rate of the air, it will be the work output, here we have it in kilowatts, divided by the net electrical work, which needs to be also in kilojoules per kilogram. Again, the rounding. This, yeah. So the work in kilowatts divided by unit work in kilojoules per kilogram, and the resulting units are kilograms per second. And now we have the how much of the fuel do we need to supply into the system. So let's calculate at first the heat input. So the heat input is the work output divided by efficiency. If it's electrical work output, so divided by electrical efficiency, which we have over here. So 240 kilowatts needs to be the heat input in the fuel. And yeah, we have the fuel in given in volumetric heating value, megajoules per normal cubic meter. So volumetric flow rate of the fuel will be the heat input in megajoules megajoules per second, megawatts, divided by the heating value. And we get, normal cubic meter per second.